Hello everybody, my name is Dave Neary. I run developer relations for Ampere Computing, which is an Arm64 vendor. And today I'm going to talk to you about why, a lot about why, like what kind of applications work well, what makes sense to run on Arm64, and then how to do the migration. And for the how, I'm not going to focus a lot on like software compilation tool chains. I'm going to focus more about cloud deployment, containerization, Kubernetes, doing workload placement, that kind of thing. Okay, well, it's presentation in three parts. First, what are some of the benefits that we bring to the table with Arm64 CPUs for the cloud? Then we're going to talk about what kind of workloads really work well and make sense to run on that architecture. And then finally, what's involved in making the change in terms of building Arm64 containers and multi-arch manifests, and then doing your workload, your application lifecycle management with Kubernetes. Okay, so why would you even consider using Ampere Arm64 CPUs? We're not the default, right? Everything you're going to run out of the box is going to be x86. So it's a change that you have to make. Change typically in people's minds means risk. So why should you even consider using this? Well, there are three main reasons. And the very first one I would say is we've built a CPU for cloud applications from the ground up. This was part of the founding principles of the company, but it's also a big part of why Arm64 is a compelling architecture for this type of application. x86 has been kind of dragging along some legacy from the 1980s and 1990s, multi-tenancy desktop applications, virtualization coming along and kind of trying to figure out how to carve up physical cores into virtual cores so that you can share computers. And a lot of that functionality that's been dragged along from the 1980s is adding power usage, and it's adding complexity that makes it difficult to manage applications running on x86 in cloud environments. And when I say in cloud environments, I mean typically in environments where you're running kind of microservice style applications where you have single compute units like a virtual machine or a container running one thing and just running it all the time. So we've built a processor that's designed basically for modern workloads, designed from the ground up for the needs of CSPs, which means we're providing high core count per socket. That gives you more compute density. It allows you to have more compute in a rack, and that allows those CSPs to rent those individual core hours much cheaper than x86 cores. So the high core count, low power, very important for CSPs. Obviously, power is kind of the constraint of the cloud right now. So by providing low power CPUs, we're reducing operational expense and we're allowing greater density in those racks. You don't have to leave empty rack slots, right? So in a 42U rack, we're actually using 40U of compute and then a top rack switch, right? So more cores per rack means less volume. Also, cloud is a real estate play, right? You have to have physical infrastructure to hold all of these computers. And so we built a CPU that's designed for the needs of CSPs, and that has a knock-on effect of having those core hours be cheaper for people who are renting them. This also applies, obviously, all of these savings in operation expense and core density also apply for people who are running Arm64 servers on-prem. And that's a key audience as well for Ampere. So one of the things that when I talk about built for the cloud, and I'm going to get into single-threaded cores and some of the benefits of that in a little while, but before, so this is a quote from 8x8. 8x8 is the company who is behind Jitsi, video conferencing software. And one of the things they noticed is before they moved to Ampere A1, they would have to auto-scale when their load on an instance hit about 60%. And that was because once you go above 60% in terms of load for an individual instance, you're hitting resource contention on that core if it's being split between two processes, if you're running vCPUs. So a vCPU with simultaneous multi-threading is you're getting a half a core, basically. You're not getting a half a core, you've got two workloads sharing one core and time sliced at the CPU level. So one of the advantages of running on Arm64 is you can actually boost the load that you put on an instance before you auto scale to a new one. So you're doing more work with fewer instances. All of the things I talked about in the last slide make it good for your pocket, right? There are some really, really compelling cost savings that can be had as a person running applications in the cloud if you run on the Arm64 instances. On pretty much every cloud right now, they're the cheapest instance that's available on the server, on the cloud. And because there's more CPUs, less power, less volume, that means that you're renting them cheaper. So a lot of the people who have been adopting Ampere, and this is a quote from Amadeus, who are running, Amadeus is the kind of the search engine behind a lot of the travel industry, searching for hotels and flights and pricing and so on. And Amadeus run a lot of that search functionality on OpenShift, on Azure, running on Arm64 instances. They wanted to move to mixed architecture. Why? There were two primary reasons. One is less power. I'll talk about that in the next slide. And the other is reducing cost. And they improved performance per price by about 40%, I think. I have a quote on it later. But yeah, basically you're running the same workload, you're getting more work out of it, and you're paying less. And I've talked about power repeatedly. It's good for the planet. We're in a situation where power is really the key constraint. And we're seeing an industry trend towards, let's see how we can power data centers of the future, especially for AI. We're seeing things like SMRs and nuclear power stations getting a lot of traction these days. So power is really the fundamental constraint of what we can do with compute tomorrow. And running lower power CPUs is one way that you can satisfy the demand for compute that we're seeing without having to add more energy sources and more data centers and more strain on the grid. We're already seeing contention between cloud data centers and residential grid usage, right? That in my country, Ireland, the power usage of data centers is now over 20% of the total power consumption of the country. In London, homes are not being built for people because the data centers are putting too much pressure on the grid. Right? So we're in a situation where we're not talking about theoretical, this is like we're hitting a theoretical maximum. No, we're talking about practical effects of we're not building homes for people because the data centers use too much power. So in that kind of world, I think being conscious of the power usage of your CPUs is important. Okay. Let's talk about what kind of applications work well on Arm64. What are the kind of applications that you should be considering moving today because it's low overhead to do so, and you'll just see benefits, right? So there's typically a three-legged stool in here. It's like, how good a fit is this? Will you see an improvement in performance or price performance over x86? How much effort is involved? Is it something that works out of the box, or are you going to have to invest a lot of engineering effort in testing and qualification? And then finally, impact. Is this something that's a big part of your cloud spend? And if it's a big part of your cloud spend and there's a good fit, then maybe it's worth the effort. If it's a good fit and low effort, maybe you don't care about the impact. But these are the three legs of the stool that you need to be thinking about when you're considering which applications to move first. So here's just a few examples, and there are others, right? I could summarize this as saying this is a general purpose CPU. You can run everything on it, and that's more or less true. There are some limitations. There are some things that are going to be harder. If your application is using a lot of platform-specific code, like x86 assembly or things like that, then that's going to be harder, right? You're going to have a little bit more work. If you're heavily leveraging things like SVE, scalable vector extensions, and you would need to re-implement algorithms in Neon, which is the Arm64 SVE or SIMD modules, then obviously there's a little bit more work involved, or you take the hit on performance. But there are a few workloads that really work well. I'm going to start with databases and caches, object caches as a service, applications like that. We have a number of case studies and YouTube videos up about this where we talk to people who basically, one of the advantages of single-threaded cores, not having SMT, is that you have the ability to very strongly limit tail latencies on latency-sensitive workloads. So object cache is Object cache is one of these workloads, like applications like Redis, Valkey, Memento is an implementation of Apache Pelican. Workloads like that, you care about the tail latencies, like the P99.9, because if you're hitting that cache 100 times per rendering a page, right? What the experience that your end users are having is not the P99 latency or the P50 latency or P75 latency. They are being impacted by the 1,000th% of those latencies, right? You can have a real user impact if you impact tail latencies. And one of the things that Memento have seen is they were able to, with an 8-core VM, drive what is the 1 million requests per second for Pelican. They've since done I think 2 million requests per second with 16 cores for Valkey. And the reason they can do that is because they're running on high performance ARM64 cores that are basically not having resource contention. They do some things in there that are kind of nice, like they will do core pinning for all of their housekeeping functions on one core. They use a couple of cores for network I/O interrupts to make sure that their caching threads are entirely uninterrupted and not having any context switches. But this is the kind of workload where you can get a massive boost in price performance, and it basically works out of the box. OCI Cache is running a really an at-scale service of, it was previously Redis and now they've moved to Valkey, all running on ARM64 because it was the cheapest option available to them. But it's not just object cache, it's not just in-memory databases that work well. Crunchy Data has seen customers, Crunchy Data is a Postgres company, and they've seen customers running their Postgres operator on Kubernetes save up to 30% by just switching to the ARM instances on the cloud of their choice. Another really obvious use case where there's benefit in running on ARM64 is when you're building stuff for ARM64, right? Either if you're virtualizing ARM64 devices for test cycles, or if you're building software that's going to run on ARM64 instances afterwards. Just a few examples here. Nissan are simulating automated, like a lot of their testing of autonomous driving software. That's all going to be running on ARM64 when it's running in a car. So they want to test it on ARM64. It's not necessarily running on a server class ARM64 chip when it's running in a car, but they want to test many instances of this in parallel. The way they do that is they're running all of their test software virtualized in ARM64 servers because they don't have the impact of cross-compilation or emulating ARM64 on x86 underneath. That would just not be performance efficient. OSMC, open source media server, open source project that basically runs kind of a media center on Raspberry Pi class software. They have to build their software and they have to test it. Well, how do they test it efficiently? They're doing so on an ARM64 instance powered by Ampere in the Oregon State University open source lab. And they saw their build and test cycle reduce from 5 to 6 hours when they were running with QEMU emulating emulating ARM64 on an x86 CPU. They saw a reduction of over 90%. They were running through their full test cycle in under 30 minutes, which is a massive performance and time gain, right? And this is one that I really like. So this guy, Lars Wickman, who's Swedish, he was, and Karen, you're really going to like this one. So he wanted to test how many VMs he could run on a single 192-core Ampere 1 server. It's basically the same workload. He's running many instances of it to do over-the-air updates of firmware on ARM64 devices. So he wanted to emulate those devices in ARM64 VMs. He ran up to 7,000. He has a blog post that says booting 5,000 Erlangs. He has up to 7,000 virtual machines. He's basically he's massively oversubscribing both memory and the processor because it's a workload that's not particularly latency sensitive, but there's massive duplication in each VM is running basically the same base image. So he's using KSM, kernel shared memory, kernel kernel, same page memory, yes. So he's basically, all of those 7,000 instances are using the same 500 megs of memory. And then, so I think he hit the total, like if you take the aggregate of all of the memory that these 7,000 VMs were using, it's over-reporting because there's duplicate in there, but he was up to a couple of terabytes. And there was not a terabyte of memory in the server, right? So if you're running this situation, if you want to emulate ARM64 server, ARM64 hardware, whether that's something like you're doing Android development or Raspberry Pi development, or you're testing software that's going to run on a Raspberry Pi, or if you want to do testing of something that's going to be running in ARM64 later, running it on ARM64 hardware kind of really makes sense. But kind of the meat and two veg of cloud computing is microservice applications, it's databases, caches, and stateless microservices, and those run really well as well. One of the reasons why the Elixir / Erlang workload from the last slide works really well is because Elixir is a functional language running on the Erlang VM. Functional languages value what? Communication over messages, immutable objects, and idempotent functions, right? You're not changing the state of the machine by running the function many times. That's essentially stateless microservice, right? Kind of design. And when you have that situation, you can massively scale across lots of cores, and you can use lots of memory, and high-speed interconnect between those cores becomes really important for your application performance. And so just a few examples. I've mentioned Amadeus already. They increased performance per price by 47%. I was underselling them earlier. And this is while increasing throughput by 20%. So they're getting more performance for less. That's actually something we heard from 8x8 as well, that they were getting 30% more performance per core running Jitsi, which is a Java application, while paying 30% less per core. Uber has done a massive migration of their infrastructure to ARM64 instances on OCI running on Ampere. The main reason is price, but their secondary reason was to meet their environmental and carbon commitments, right? Moving to a more power efficient processor is a big win for on multiple axes. And AI inference. Everything is AI all the time these days. And our contention is that if you give people a lot of cores that are all running at 3.5, 3.3 gigahertz, right, which is not going to be teraflops, but it's going to be, you basically get one floating point operation per cycle on modern CPUs. That's about 3 gigaflops per core, but you've got 192 of them in a server. All of a sudden, you can do a lot of compute, right? So for a lot of, I would say a lot of AI inference workloads that are basic machine learning workloads, repeatedly applying something like a neural network with reinforced learning for a recommendation engine or a chatbot or object recognition or automated transcription of speech to text. Those kind of applications don't need GPUs to run at a specific performance. You can get it. Basically, I would argue you want to choose the hardware you're going to run your AI inference on based on the SLO that you have, right? How many people are going to be using it? How quick do you need an answer? We've seen with small model LLMs and with a lot of machine learning workloads that you can run them perfectly adequately. Like, it's not going to be the same performance as if you're running on a Blackwell 200, or I don't even know the code names. I shouldn't wing these things, but you're going to be running with less power, cheaper, with the ability to take advantage of scalability on your application. When you get more users, you can scale out to more cores. You've got more incremental scaling, and you're basically saving a ton of money. So 2 examples, scientific applications. There are a bunch of these that are basically doing image classification and some things like automated image identification of, like, identifying cancer cells in MRIs and things like that. For those kind of image classification, image analysis workloads, you can get the best price performance out there and the best bang per buck, if you like, is running it on CPU rather than GPU. You don't need to use GPU for those workloads. Something like a RAG enhanced LLM, where you're going to do a chatbot that's got a low volume request coming in, or maybe you want to run an LLM on the edge where you don't necessarily have access to a lot of power, a very expensive GPU. You can run that on a CPU perfectly adequate. Okay, so that was a lot on the what you might change. Let's look at what's involved in the how, right? So when you're building and deploying a cloud application, by the way, may I have just a time check? How long do I have left? 15 minutes. I'm going to 55. Excellent, thank you. So let's look at what's involved in building and deploying an application, right? This is all kind of continuous delivery style flow, but you've got a source code commit for your actual application. The application gets built. So to build your application, you want to provision a build environment, do your build, run your tests. Then you've got provisioning a test environment. You're going to do your packaging of your application, deploy your application to the test environment that's going to match production, run all of your functional integration tests, performance and load tests, and then you deploy to a production style environment, so sort of pre-prod environment. And you want to have all of this automated. The light squares are the ones where the architecture really doesn't matter very much. The darker arrows here are where you have to think about the architecture. And I'm certainly going to focus a little bit more on what's involved in provisioning environments and deploying the software. So it's going to be more about the how do you do the actual deployment and testing. So there are a few gotchas in here. There's a lot of layers in the container layer cake. I'm sure anybody who's done container application development has come across some of these things. You know, you're building a container. You need to make sure that that it will run on the architecture you're targeting. Container repositories do have to be they are architecture aware through tags and manifests. Then you want to make sure that you're doing workload placement correctly with Kubernetes YAML. And then if you're running with something like GitOps, like an Argo CD on the top, you want to make sure that you're managing the application lifecycle appropriately. Okay, so what are the gotchas that you've got in there? Layers 1 and 2, building multi-arch containers. So a multi-arch container, can I get a show of hands who knows what a multi-arch container manifest is? Okay, it's worth explaining then. So containers, obviously, are compiled binary objects for a specific target architecture, right? If you're compiling software and you're making a Docker container, if you're running a Docker file and building a new, or a container file and you're building a new OCI container object, that is going to have binaries in it. Those binaries have been compiled for a specific architecture. Now, what you can do is you can have binaries compiled for different architectures that are then combined into what's called an application, multi-architecture container manifest. What that is you've got one line with a SHA key per container that says this container is for x86, this container is for Arm64, this container is for PPC64. And when I do a pull of the manifest, what it does is basically that's a pointer. It says, oh, you're doing a pull of this container manifest on Arm64. I need to go and get the Arm64 containers, and then it pulls the right SHA. That's how that works. But you need to have all your to get started, you need to have all your binaries compiled for all architectures. You can do that with something like a Docker buildx or Podman buildx. Does Podman have buildx? Okay. But you can do there are things that exist in the pod. I know there are Podman. I think I have a slide on this later, where how you build your containers, and thank you, how you build your containers and deploy them to the right architectures. The easiest way is you independently build your Arm64 and your AMD64 containers on the right host architecture, and then combine those container SHAs into a single multi-arch manifest. Creating your multi-arch manifest with Podman, I told you. So you can do your build with platform Linux Arm64. Linux ARM AMD64, and then once you push your images into your quay, you can create a manifest and add those images into the manifest afterwards. There are some gotchas here. If you keep adding into the same manifest, you will have duplicates for each platform. You need to wipe the manifest before you kind of add each of the images when you're creating a new version. You can do that as separate images, or you can do that in a single step using, Podman build minus platform, and you give it just multiple platforms, and it knows how to build on them. I don't know how that works. Some of the best practices, you want to build your images separately on native hardware rather than doing cross-compilation. Be very careful of tagging. Like I said, it's very easy to replace a multi-arch manifest with an AMD64 binary container. I've seen this happen multiple times when people are kind of short-circuiting CI processes because they have to get a quick fix into something. They push the container to the tag, which is unassociated with an architecture, and they end up overwriting a manifest with a binary container. Happens a lot. Be careful of it. Also, I, for one, have spent a lot of time staring cross-eyed at a manifest file only to notice that AMD64 and ARM64, one of them was spelt wrong, right? They look really alike. So it's important. Okay, that's all I'm going to say about building. I know there are probably some questions about building, but I'm kind of running shorter on time, so I'm going to carry on to layer 3, which is Kubernetes and Kubernetes YAML. So a typical Kubernetes application contains a bunch of YAML files. It defines higher level objects that are services. It's got secrets and config masks, etc. But I'm going to focus on the deployment, replica set, pod. Kind of the motor of a Kubernetes object is the thing that's going to run a container, right? And pods run containers. Deployment sets run collections of pods. Replica sets run collections of pods. Deployments deployments manage replica sets. And I don't think enough people know the difference between a replica set and a deployment. So I'm going to briefly explain. A replica set basically ensures that you have a certain number of containers of a given template, which you specify in your Kubernetes YAML with a given label. Right? What that means is that if you change the container image and leave the same label, and you say, I just want 3 replicas of, and you change the version to version 2.0, and then you kill one of the 1.0 containers that you were running, it'll start one copy of the 2.0 to make sure that you have the right number running. Replica sets only use their template when they're starting new containers as part of the replica sets. Deployments, on the other hand, manage replica sets, not containers. So the way a deployment works is you've got one replica set running the old container. If you deploy a new version of that deployment, which has a different image or a different tag or different metadata, it's going to start a new copy of that replica set. And there are 2 criteria that you need to be aware of. One is max surge. That's the maximum number of containers above the total target number that you're going to have, because you start new containers in the RS2, and then as they get healthy, you shut down containers in RS1. So there are 2 criteria. You want to make sure that you have a you limit how many extra containers you can have running in the new replica set, and you limit how many containers you kill in the old replica set before you consider the service not sufficiently available. Why is this important? It's important because when you're deploying to ARM64, you're going to use workload placement rules to deploy your new containers to your ARM64 containers to ARM64 nodes. So we use labels to mark a node with a specific capacity or restriction in node selector. And I'm actually going to recommend you not use node selector. I'm going to recommend that you use something else in a second. But you can tag nodes with, this is an ARM64 node, this is a node with SSDs, this is a node with a GPU. And then you can make sure that when you're selecting nodes for a container, that the containers are matched with a node that has the capacity that they want. There is a second way that you can do workloads, which is taints and tolerations. So you can taint a node and say this node is only available for certain types of workloads, and then you can have a toleration on a pod where it says, oh, I accept running on this other thing, but I prefer to run on this first constraint. And you can use taints and tolerations to manage things like memory pressure, I think. Memory pressure, CPU pressure, etc. So taints are used to prevent scheduling for busy nodes with memory pressure, disk pressure, PID pressure. I was right. And they can both prevent new workloads from being scheduled, and you can force eviction, right? If I hit a limit and I'm, all of a sudden I'm out of memory, I can kill or evict workloads that are using a lot of memory. So it's one way that you can do workload placement. But this is the way that I would recommend, is using affinities. So node affinities are similar to node selector, but you basically say, I would prefer this, but I have a fallback to this other thing. So on this situation, for example, I'm running, I've got a node affinity associated with my container template. I'm going to match on the kubernetes.io/arch architecture, and I'm going to prefer ARM64, but if there's no ARM64 available, I'm going to run AMD64. Really nice way to run multi-arch containers and to make sure that your application is available, even if, for example, there are no ARM64 nodes available when you want to start up a new instance. And now I'm rushing through this, which I shouldn't do. I'm going to recommend that if you want to do an application migration, right, you've got an application running on AMD64 nodes today, right, with x86 64, and you want to start moving incrementally. Let's say moving your Redis cluster to ARM64, or let's say moving your MySQL database to ARM64. This is something that's easy to do. You can use, I really like Argo rollouts for this. If you're using Argo CD, then it's an easy sell. If you're not using Argo CD, you can still use Argo rollouts. And the way Argo rollouts do is they have a new kind, which is basically a superset of deployment, which is kind rollout. And it basically, like I said, it's a superset of deployment. So you're doing the same thing as deployment did, starting a new replica set, starting containers with the new template in the new replica set, and shutting down containers in the old template, in the old replica set, based on availability rules, surge and max unavailable. But it also includes this neat section, which is strategy, which it kind of encapsulates some of the best practices of continuous delivery rollouts, where you can say, I'm going to do blue-green. I'm going to start up a completely new cluster, and I'm going to transfer all the traffic. It does all the traffic management for you, and there are different ways of doing traffic management in Argo rollouts, but it's going to say, I'm going to start up the new service, and when it's fully available, I'm going to transfer all the traffic over. You can do Neary builds where you say, I'm going to transfer 5% of the traffic over when it gets to 20% of the cluster of the containers running, and then I'm going to wait until I've verified some kind of acceptance tests, and then I'm going to transfer over another 20%, and then I can do more acceptance tests, and I'm going to transfer over 100% at that point. So there are a number of ways that Argo rollouts really makes things like doing, like if you've ever done this with deployments, you know it's a pain in the ass, right? But doing it with Argo rollouts is really easy. Canary deployments. This is kind of So this is the way it defines us. Canaries is you say how many each of my steps. I'm going to go step up to 10%. I'm going to pause. I'm going to wait 60 seconds, and then, or you can even have an acceptance test where you say I'm going to wait until this test passes, and then I'm going to go to the next stage. So really, really nice way to do AMD to ARM64 migration. This is before we're going to have a node affinity that says I want to run this thing on AMD64. By simply changing that to ARM64, if you're using Argo rollouts, by simply changing that to ARM64 and rerunning your rollout YAML, all of a sudden, hey presto, your Nginx is running on x86, or your Nginx is running on x86 on ARM64, your Redis or Valkey is running on ARM64, and you didn't have any migration work to do at all. And I think I'm out of questions, but I want to point people at the Ampere Developer Center, amperecomputing.com/developers. We have a YouTube channel which has a whole range of videos of people talking about their experiences migrating to Ampere servers and some of the benefits they gained from that and why they did it. I advise you to don't listen to me, listen to people who've gotten advantage from it. And I'm looking forward to seeing you all using Ampere in the future.